Everyone. Welcome to Physics 2211 Lab 5, and today's lab is going to be about the slinky falling from Veritasium's video. And I'm Sadev Bharat and I'm going to be presenting this. So the introduction is simple. We want to determine when a slinky reaches the ground, the bottom part specifically, and we have a video given by Veritasium, and we will first analyze this using tracker and then trying to plot it in GlowScript. So the fundamental laws involved are simple. We have the universal gravitational formula, which states that every particle in the universe attracts every other particle with a force along a line joining them. Newton's first law, which states that an object will remain at rest or in motion at a constant speed unless an external force acts upon it. And Newton's second law, which states that the acceleration of an object depends on its mass and the force applied. The main formula involved are simple. We have the universal gravitational formula, which is negative g m1 m2 by r hat. We have Newton's first law, which is Rf is equal to Ri plus V average delta T. And Newton's second law, which is Vt is equal to V naught plus Et. So our setup is simple. We have the main experiment, which is initially a recording from YouTube analyzed using Tracker. Then we created our own GlowScript code to try and simulate the slinky falling. And our initial conditions are the position is 0, 0, 0, velocity is also 0, and the time for the initial drop is 6.267 seconds, and the second drop where the drag force is added is 8.867 seconds, and our delta t is 0.033 seconds. So the preview and methodology is as follows. We have the system, which is the slinky as an object, and Earth, which has gravity, and then our surroundings, there's nothing in the surroundings. Mass of the slinky is 0.215 kg, and this was found via Google for the average weight of a slinky, and the gravity is 9.8 meters per second square. And the model and the experiment had quite close data correlation, but there were some errors due to technical errors in the tracker data. So this is a tracker video. As you can see, the bottom part does not move while the top keeps moving downward. And then right as everything comes together, the bottom also starts moving and our y-axis starts going downwards, which is what we wanted. So this is basically the tracker video and the Veritasium video. So now this is the code that I made. So we have the slinky, which I defined above, a trail, the graph, and now these are parameters. We have 0.215 mass in kgs. We have gravity. We have the initial position vector, the initial velocity. We have time, delta t, our j hat vector, and b, which is our drag force. This is the important one that makes the difference in our second while loop. This is our first while loop where it's just the top part of the slinky falling all the way to the middle part, and we just use the change in fnet. We have our position update and velocity update formula, and we have our time update formula as well. Here, this is the second one, which is with damping, and as you can see, we've added the negative d, and we've added the normal force as well, which accounts for the damping force. And then again, we do velocity update and position update and update the time as well. So this is the data from GlowScript. So as you can see, it matches our original y hat vector in the tracker data, and it slowly starts going down, 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 all the way to negative 0.35 meters. And this matches our tracker data for the most part. These small dridges that you see are basically the damping force that is coming into account. So when we look at our final data, by the comparison of the tracker data and the GlowScript code, there are definitely some errors. As you can see, the final data didn't exactly match the meters in both the tracker versus the video. And this is mainly due to the errors in tracker, which were like an error on my end, because while calibrating and fixing the tracker data, it was quite a challenge as the background of the slinky video blended in with the slinky and made the tracking quite challenging, so the auto tracker wasn't working very well. And then other than that, the overall structure of the data matches on both fronts, while only for a misalign on the actual meters. So if you look at our actual questions, the slinky at the bottom part stays stationary even though the top of the slinky moves down. This is primarily due to the forces in the y direction cancelling out. So we have the gravity in the negative y hat direction, and in the positive y hat direction we have the spring force, or like the tension force of the slinky upward. So these two cancel out basically. The tension force and the gravity force end up being equal, which is why the bottom part of the slinky remains stationary as the top moves down. So this is basically why the slinky keeps moving downward while the bottom of it never moves, but right as the top reaches the bottom also moves downward. Thanks a lot. That's my 2211 Lab 5 final lab for Physics 2211.